Okay, in this chapter, chapter number 7, we'll talk about chemical changes. Now, a chemical change occurs when a substance is converted into one or more different substances, and they have different chemical properties and different chemical formulas. Now, some of these are easily observed: formation of bubbles, a change in color, a change in odor, production of heat or production of a solid. So anytime you get a new set of chemical properties or a new chemical formula, then you have undergone a chemical change. An example that's given here: a silver fork that's been tarnished. The silver, Ag, is turning a different color because you're adding sulfur to it. And that's why rust has a different color to it. You're actually forming a new compound through a chemical change. The tarnished on silver is a different product that is being produced. It is a chemical change. Alright, next we'll focus a lot on the writing of a chemical equation. All chemical equations, no matter how simple they are, no matter how complex they are, all boil down to two main components. You have the reactants, and the products. This stuff here is reacting or combining together to create a product. So no matter how involved these reactions can get, it all boils down to those two main categories. Stuff reacting together to form one or more products. And you'll see that this arrow is here. This arrow means this stuff will yield or give you this product. An example here: carbon plus oxygen. These react together and give you or yield carbon dioxide. That's the product. Alright, to write a chemical equation, that arrow is what will separate the reactants from the products. Everything to the left-hand side of the arrow are reactants. Everything to the right-hand side of the arrow are the products. And if you have multiple of either one, they are separated by a plus sign. One plus another. Sometimes above the arrow you will see a triangle shape. That is the delta sign. And when you see this with a chemical reaction, that indicates that heat is used in that reaction. So for this example, this reactant plus that reactant combined together with heat added will give you these two products. Now, some elements can exist in more than one physical state: solid, liquid, gas. So you have to indicate what form of that element or compound that you're talking about, so you can be as clear as possible. So for example, water, H2O. If you see water in an equation, well, that could mean liquid water, it could mean water vapor, the gas form, or it could mean solid ice, the solid form. So you need to indicate those physical states just behind the compound you're talking about. So to indicate solid, you would put S in parentheses, liquid, lowercase l in parentheses, gas, lowercase g, or aqueous, which means being dissolved in water. And there's a good summary of all these symbols that you would see with any chemical equation. Plus, separating two or more reactants, two or more products on the equation. The yield or the arrow sign. The arrow with the triangle or the delta symbol shows that reactants are heated to give you the products. And solid, liquid, gas, aqueous. Alright, now we'll move on to identifying a balanced equation. In a balanced chemical equation, no atoms are either lost or gained. The number of atoms you start off with in reactants will equal the same number of atoms in the products. So you can't have mass just disappearing for no reason. You can't have mass just appearing for no reason. What you start off with is what you'll end up with. It may be in a different form, but the number of atoms does not change. So in this example here, you have one atom of carbon, two atoms of oxygen. When they combine together, they form one product, carbon dioxide, but you still have one carbon here and two oxygen. This is a balanced equation. Even though there are two reactants, one product, the amount of stuff has not changed. There's still one carbon on both sides of the arrow. There's still two oxygens on both sides of the arrow. So nothing has changed. Alright, now we'll move on to balancing a chemical equation. And some of these can be fairly straightforward, but when you get into fairly involved chemical reactions, especially those involving polyatomic compounds, it can get really complex. The reaction we're talking about: aluminum in a solid form plus sulfur in a solid form. These are the reactants. They combine to give you Al2S3 in a solid form. Now, just looking at this is a unbalanced equation. Over here you have one atom of aluminum on the left-hand side, but two on the right as a product. For sulfur, there's 1 on the left-hand side, but 3 on the right-hand side. These are not balanced. So in order for an equation to be balanced, you have to find a way to rewrite this equation where you aren't changing the core of the reaction, but you're changing how it's written, so the numbers do balance out. And the way you do that is you add what are called coefficients to the beginning of each element. And you do that until all the atoms of every element are equal on either side of the arrow. So for this example here, if you add a 2 before aluminum, now on this side there are 2 atoms of aluminum, and there are 2 atoms of aluminum on the right-hand side. That is balanced. For sulfur, you need to add a 3 as a coefficient before it. 3 atoms of sulfur on this side, and 3 on this side. These are balanced. And again, you aren't changing the whole core, the whole process of the reaction. That hasn't changed. The only thing that you're changing are the coefficients in front to make it a balanced equation. Now here's what I was talking about with how involved it can be. We're talking about polyatomic ions. Given this very involved, very complex equation, the way it's written now, it is not balanced. This is a quick glance. Sodium over here has 3, but sodium over here only has 1. What can make this time-consuming and complex is that every element has to be balanced. If one element is not balanced, that means the whole equation is not balanced. So you could get all of these, but maybe say sodium, but if that sodium is off, then the whole thing's wrong. So everything has to be balanced. But it's the same process that we did with the previous reaction. You can break it all down. So again, sodium, there are 3 of those here, but only 1 over here. You can break these down by individual elements, like for example, phosphorus and oxygen. But if they are forming an ion together, like they do in this case, you can do it that way also, and that usually will save time. So PO4 is one ion. So there's only 1 of those on this hand side of the arrow, but there are 2 on this hand side of the arrow. That is unbalanced. Magnesium, there's only 1 on this side. There are 3 on this side. And then for chlorine, 2 on this side, only 1 on this side. So there are 4 components of this reaction that are not balanced. All 4 need to be balanced for the full equation to be balanced. You can't just do this one, and this one, and ignore sodium. If one of these isn't balanced, the whole thing is wrong. And the best way to do this is really just trial and error. Keep adding coefficients until you get equal numbers of all elements on either side of the arrow. And the way you would do that here, for sodium, we start off with 3. If you add the 2 in front, 2 of these 3, 2 times 3 gives you 6. Then add a 6 over here to balance that out. Alright, for the PO4, there are now 2 groups of those on this side, because this 2 is applicable to both components of this compound. So 2 over here on the left-hand side goes with the 2 that was already here on the right-hand side, so they're now balanced. You add the 3 in front of magnesium, so that equals 3 on this side. And the 3 that were already on this side, so now they're balanced. For chlorine, 3 times the subscript of 2 gives you 6, and it goes along with the 6 that you just added over here for sodium, so now they're balanced. And again, you aren't changing any part of the reaction given to you. All you're doing is adding coefficients to make the equation balanced. And again, for the final step, going back and making sure all the coefficients match up. And again, if one number or one element is off, then you need to go back and recheck. Sometimes coefficients need to be changed, but you can't change these subscripts. You can't change the 3 for the sodium, or the 4 for the oxygen here, or 2 for the chlorine, or 2 here. Subscripts you cannot change. What you can change are the coefficients. The 2 here, 3 here, and a 6 here. Those you can add. Alright, now I'll move on to different types of reactions. There are multiple forms of reactions, and any reaction can be more than one of these categories. It just depends what is going on. The first one, a combination reaction. Sometimes this is called a synthesis reaction. This is where you have 2 or more reactants forming one product. You are combining 2 things to make one product, or you're synthesizing one product. The opposite of that would be a decomposition reaction. When something decomposes, it breaks down. So you're taking one larger reactant that breaks down into smaller components. So the exact opposite of decombination. Single replacement reactions. This is where you have one element will take the place of a different element in the reaction. You'll see an example of that on the next slide. Double replacement. The positive ions in the reactants are switching places with one another. And for the last one on this page, combustion reaction, this is where you have compounds that have carbon in them that will burn in oxygen gas to help form carbon dioxide, which is CO2, and water, H2O. It's a nice way to visualize both a simple way how to write those types of reactions and an example that's given. The first one, combination or synthesis. This reactant plus that reactant gives you one larger product. So calcium plus chlorine gives you calcium chloride. For these types of reactions, there's more items on the left-hand side of the arrow versus the right-hand side because you're forming one larger product. The opposite of that will be decomposition. The reactant AB is breaking down into A plus B. So for this type, you'll have more items on the right-hand side of the arrow versus the left-hand side. So this example, Fe2S3 breaks down into iron and sulfide. A single replacement, A plus BC. Those reactants will break down to give you the products AC plus B. So we're just using the this is regular letters. A is by itself, and you have BC together. But as a product, A and C now are together, and B is by itself. You are switching places here. One element has been swapped out. So an example that's given here, Cu plus AgNO3. As a product, copper is now joined with NO3, and now silver is by itself. This has swapped places here. So Cu and NO3 are now together. So one element is swapping or switching places with another. And for double replacement, AB plus CD gives you AD plus CB. Instead of one element switching places, you have two switching places. An example that's given, BaCl2 plus K2SO4. As a product, Ba is now joined up with SO4. And then chlorine is now joined up with potassium. The elements are still there, but they're switching places. And for both of these, single and double replacement, you have the same number of items on the left-hand side versus the right-hand side. Because you're not breaking anything down, you aren't forming something larger, you're just switching places with various elements. And for the last one, combustion, a carbon-based compound, here, methane, added to oxygen and then burning, because you're adding heat, gives you carbon dioxide and water and energy. Alright, next we'll move on to a different class of reactions, oxidation-reduction reactions, or redox reactions. Now these are incredibly important, incredibly common. This is how we get energy from the food that we eat, that turn into glucose that we eat into a usable form of energy for our cells. It will help provide energy in batteries. And also what will give you rust with iron. And that's what this equation is showing. The solid form of iron, say on the bumper of your car, plus oxygen in a gas form, that over time gives you iron oxide, a different compound, which is that reddish brown color, which has undergone a chemical reaction. Now in any oxidation or reduction reaction, electrons are going to be transferred, either by losing an electron or by gaining an electron. So oxidation is the loss of electrons, and reduction is a gain of electrons. So for oxidation, the compound will get more positive, and for reduction, you're getting more negative, because you're gaining electrons. Now it's very easy to get these two situations confused, and there is a common saying that's used, or common mnemonic used to help remember what goes with what. Fairly simple, it's kind of silly in a way, but it's also very effective. And that phrase is, Leo goes grr. Leo, the lion, when the lion roars, he goes grr. So the first one, Leo, losing an electron is oxidation. The opposite of that, grr, gaining an electron is reduction. Leo goes grr. So again, pretty silly, pretty simple, but also very effective. A famous example of an oxidation-reduction reaction is the Statue of Liberty, and how it has that very distinct kind of a pale mint green color to it. The outermost layer of the Statue of Liberty is a version of copper called copper carbonate. Now as this layer oxidizes, it forms a green solid, copper oxide. And here's how the Statue of Liberty gets that color. You have the solid form of copper. As it breaks down, it becomes oxidized. That combines with oxygen gas, and those two components combined together gives you copper oxide. It's the same process as iron rusting, like on an old car. It forms a new compound that has a different color. That's what gives rust its distinct reddish brown color, is a new compound being formed. It's the same thing with the Statue of Liberty. It's how it gets that greenish hue to it. It's forming a new compound, copper oxide. Next we'll talk about characteristics of oxidation and reduction. Now the particular definition of these types of reactions depend on what is occurring in the reaction. For oxidation, it always involves a loss of electrons. Remember that phrase Leo, losing electron is oxidation. It may also be seen as the addition of oxygen, and may also be seen as the loss of hydrogen atoms. For reduction, it will always include the gain of electrons. Remember, Leo goes ger, GER, gaining electron is reduction. Reduction may also be seen as the loss of oxygen, and may also be seen as the gaining of hydrogen atoms. Alright, next we'll move on to what's called the mole. Now this is a very important term to understand, and it really is just a counting term used in chemistry. Counting terms that are very, very common, such as dozen, and case, and gross, and so on. Examples that are used here: 24 cans equals 1 case, 144 pencils equals 1 gross, 144 of anything equals a gross of something, 500 sheets of paper equals 1 ream, 12 eggs equal 1 dozen. So the mole is a counting term in chemistry. Now very small particles like atoms and molecules and ions are very, very high in number. So there has to be an easier way to count them, or an easier way to represent such a large quantity. Small particles such as ions and molecules and atoms, because they exist in such high numbers, there's a counting unit called the mole that's used to represent them. And that mole is represented by what's called Avogadro's number. That number represents 6.02 times 10 to the 23rd power. Very, very large number. And here it is written out. This is an excellent example of why scientific notation is a much easier way to represent really, really big numbers or really, really small numbers. Trying to write this number out all the time would be incredibly cumbersome, would be a waste of time, and be very easy to leave off 1 or even 2 of these zeros. But just like we talked about in a previous chapter with scientific notation, for this whole number, the decimal will be right here. So 3, 6, 9, 12, 15, 18, 21, 22, 23. This very large number is exactly the same value as this. So that is called Avogadro's number, named after the Italian physicist from the 19th century. So 1 mole of anything represents 6.02 times 10 to the 23rd power. Here are some examples of what I'm talking about. So 1 mole of any element equals 6.02 times 10 to the 23rd atoms of that element. So 1 mole of carbon equals 6.02 times 10 to the 23rd atoms of carbon. 1 mole of sodium, 6.02 times 10 to the 23rd atoms of sodium. So the mole value is a constant value that doesn't change. And now we'll move on to calculating moles and elements in any given formula. Now the chemical formula and their subscripts will specify the number of atoms and also the number of moles that are found. So this example that we're given, aspirin, C9H8O4. This example, the 9 that goes along with carbon represents 9 atoms of carbon, but also represents 9 moles of carbon. For the 8 for hydrogen, that represents 8 atoms of hydrogen and also 8 moles of hydrogen. And for oxygen, the 4 that goes along with it, 4 atoms of oxygen also represents 4 moles of oxygen. Now the subscripts are going to be used to help you write conversion factors for each mole and each compound. And this is something that we'll talk about in greater detail here in a few minutes. So for 1 mole of aspirin, C9H8O4, don't think of these as fractions, think of these as ratios, because that's what you're talking about. You're comparing mole to mole. So for every 9 moles of carbon, you get 1 mole of aspirin. For every 8 moles of hydrogen, you get 1 mole of aspirin. And so on and so on. And we'll revisit this topic again in a few minutes. But all you're really doing here are having a mole to mole ratio. Alright, now we'll move on to molar mass and calculations. The molar mass of an element is very, very useful to convert moles of an element to grams, or the other way from grams to moles. And it's simply represented by the atomic mass found on the atomic periodic table of elements. So for example, zooming in on information for sodium, the symbol Na, atomic number 11, the atomic mass 22.99. So 1 mole of sodium will have a mass of 22.99 grams. And this process is true for any element in the periodic table. 1 mole of that element equals its atomic mass. So for the molar mass is what we just talked about regarding sodium. So we'll zoom in on carbon, atomic number 6. 1 mole of carbon is 12.01 grams. This is what this ratio is representing. 1 mole of carbon is the same thing as 12.01 grams of carbon. For lithium, atomic number 3, 1 mole of lithium is equivalent to 6.941 grams of lithium. That's its atomic mass. So don't think of these as fractions, think of these as ratios. Again, this is true for any element in the periodic table. If you know the atomic mass, you know how many grams there are in 1 mole of that element. So 1 mole of silver will be represented by 107.9 grams. 1 mole of carbon, 12.01 grams, and 1 mole of sulfur, 32.07 grams. In this flow chart here, all three of these values are equivalent. 1 mole of carbon is the same thing as 12.01 grams, which is the same thing as 6.02 times 10 to the 23rd atoms of carbon. Those are equivalent values. It's using different units. Because 1 mole of anything equals Avogadro's number here. So these are, all three are equal. Alright, just to show you some comparisons of what 1 mole of various things would look like and how they would compare to one another. In this picture you have sulfur, iron, salt, potassium dichromate, and sucrose. In each of these beakers you have 1 mole of that sample. So 1 mole of sulfur, 32.07 grams. 1 mole of iron, 55.85 grams. Table salt, sodium chloride, 58.44 grams. Potassium dichromate, 294.2 grams. And then sucrose, which is a form of sugar, 342.3 grams. These are all based on atomic mass also. That's why the numbers of grams are higher for compounds that are larger like this, because what you're doing is adding up the atomic masses for each individual component. So for sucrose, for example, you're adding up 12 carbons, you're adding up 22 hydrogens, 11 oxygens. So if you add up the atomic mass of 11 of oxygens, 22 of hydrogens, and then 12 of carbons, all that total together gives you 342.3 grams. Now we'll move on to the law of conservation of mass. This indicates that in a normal chemical reaction, matter can't be destroyed and can't be created. It doesn't just vanish, it doesn't just appear somewhere. There has to be no change in total mass. Now the versions of those products or reactants may vary, but the mass of the reactants must equal the mass of the products. Right, here's an example of what I'm talking about. The reaction you're given, silver plus sulfur, silver sulfide. So you're looking at just the atoms. There are 2 silver atoms on this side, and there are 2 on this side, so that's fine. 1 sulfur over here, 1 sulfur here. So they're balanced, they're fine, they haven't changed. Then we get down to the bottom, where you're comparing the mass of both reactants and products. The mass of 2 moles of silver plus the 1 mole of sulfur. That added together gives you 247.9 grams. If you add up the mass of the products, Ag2S, 2 silvers plus 1 sulfur, also gives you 247.9. Even though there are 2 reactants and only 1 product, the masses are equal. Alright, now move on to the mole-mole factors of an equation. Now these are ratios based on are given to you in an equation. The example that's given here, the coefficient 2 along with iron, coefficient 3 for sulfur, gives you Fe2S3. When you're comparing the ratio between iron and sulfur, for every 2 moles of iron, you get 3 of sulfur, 2 and 3. Or if you're comparing it the other way, for every 3 moles of sulfur, you get 2 for iron. All you're doing is writing the coefficient. Right, comparing iron, and then Fe2S3, for every 2 for iron, you get 1 mole of this whole thing, Fe2S3. If you're looking at it the opposite way, 1 mole of this, because there's an understood 1 here, is equivalent to 2 moles of iron. And lastly, sulfur and Fe2S3, for every 3 of this, there's 1 of this. And for every 1 of this, there's 3 of this. All you're doing is writing a ratio of the coefficients for that compound, or for that element. Now, being able to do this is critically important when you're asked to calculate the number of moles in a reaction, calculate the amount of mass for a product or a reactant. And here's how you would go through that. So if you're given a balanced equation, if you need to convert the mass of substance A to substance B, what you do is convert the mass that you're given for substance A to moles by using the molar mass of A. You convert that to a mole for B by using the mole-mole ratio. Once you get that, you convert the amount of moles for substance B into grams for substance B. And we'll go over an example of how that kind of question would look and how you would solve it. Here's a flow chart on how that last slide would look. You're given the grams of substance A. You convert that using its molar mass to get the moles for A. You do the mole-mole ratio comparison between B and A to give you the moles for substance B. Use the molar mass to get the amount of grams for substance B. Here's how a typical question asking about moles and grams would be presented to you. So this example here is a fairly common one. Alright, here's a sample question. You're given the reaction here. Now, C12H22O11, which is sugar, plus oxygen, will give you carbon dioxide and water. So what you're given is 10 grams of sugar, and you're going to be asked to find how much in mass of oxygen is used. Following our slides, this part here is for our example here. This will be A, and then that will be B. Okay, and here's how you do that. Okay, the 10 grams of the sugar that you're given, and you multiply that by the equivalent value of 1 mole of sugar times the molar mass. If you take 12 masses of carbon, add that to 22 masses of hydrogen, add that to 11 atomic masses of oxygen, you get a total of 342.3 grams of sugar. So these are equivalent. And the reason why you have mole on top and grams on bottom, that way the grams here will cancel each other out. So what you're left with is 0.02921 moles of sugar. That's how much 10 grams of sugar will give you. Alright, that's the first part. Now you need to take this and do a mole comparison. Alright, starting with the value we just found, 0.02921 moles of sugar. And the equation up here, 12 moles of oxygen, because the coefficient is 12, so the 12 will go there, versus the 1 mole of sugar. And again, the reason why you want moles of oxygen on top, because that's what you're wanting. What you want to cancel out and get rid of, you put on the bottom of these ratios. So for here, the moles of sugar will cancel each other out. So what you're left with is moles of oxygen. So 0.3505 moles of oxygen. Okay, now we have one more step. Right, starting with the value that we just found, 0.3505 moles of oxygen. To convert moles to grams of sample. The atomic mass of oxygen is 16, but we have 2 of those. So 2 of those will be 32 grams. Again, we want the unit that we want to get rid of on the bottom of this ratio, so it can be cancel each other out. So our final answer, 11.22 grams of oxygen. So this whole process, the substance A will be the sugar, substance B would be the thing that we're trying to solve for. In this example, grams of oxygen, so 11.22 grams. Okay, and here are all 3 steps. Put side by side by side, 10 grams of what you're given. You convert the grams that you're given to how many moles of what you're given. Take that value, do the mole-mole comparison in the equation that you're given. what you want to solve for is the substance B. In this example, it would be the oxygen. So that value to go on top. 12 versus 1. That gives you the moles of oxygen. That value, convert that to a number of grams per oxygen, which is what you want on top, and it gives you your final answer. And that's a very typical, very common question when you're asked to find grams versus moles or vice versa. Alright, now we'll move on to the heat of reaction. And the heat of reaction is the amount of heat that is either released or absorbed during a reaction that takes place at a constant pressure. Now, the change in energy will occur when bonds are broken or products are formed or reactants combine with one another. And the heat of reaction is also called enthalpy, and it's written by the symbol delta and then H, capital H in italics. Whenever you see that symbol delta or that triangle, that means the change of. So this is literally written down as, can be translated into the change of enthalpy or the change of the heat of reaction. And this is really just the difference between the enthalpy of the products and the enthalpy of the reactants. So this is a mathematical way you would write this. So enthalpy equals enthalpy from the products minus the enthalpy of the reactant. There are two main types of reactions, either or based on if you release energy or absorb energy. The first one, exothermic. Exo means outside, so exothermic. Thermic means heat, so this will translate into releasing of heat. So in this example, the energy of the products is less than the energy of the reactants because heat is a product. So this is where energy gets released. So for here, hydrogen plus chlorine gas, hydrochloric gas, and also energy, 185 kilojoules of energy. Whenever you release heat as a product, as an exothermic reaction is, you'll have a negative enthalpy. The opposite of that would be endothermic. Endo always means inside, and again, thermic means heat. So this is where heat gets absorbed. So the energy of the products is higher than the energy of the reactants. So heat is a reactant. Heat gets added to the reaction. So for example here, nitrogen gas plus oxygen gas plus energy, 180 kilojoules, will give you nitrogen monoxide. So because you're adding heat to it, heat is being absorbed as a part of the process, as a part of the reaction. It's going to be endothermic, so a positive enthalpy, so 180 kilojoules.